Oh yeah, we are looking at a semicircular lens with a light ray coming in, and we're going to try to determine total internal reflection. And hopefully this time I remember to turn the sound on the video. Oh yeah. Okay, so here's the idea. Laser's coming in, and you can see there's a refracted beam coming out, and I'm going to hit the light so you can see this a little bit better. Not trip in the dark. And hopefully this shows up. You can see that there's a reflection coming out here, right about there. And then as I rotate this lens, you can see things change a little bit. And what I'm going to do is I'm going to keep rotating this until at some point the refracted beam is getting almost parallel to the surface. Let's keep going. Right about there. We can see the refracted beam is almost perfectly parallel to the surface, and then I'm going to go just a tiny bit more than that till it disappears. The refracted beam, right about there, it's disappearing. Okay, I'm going to turn the lights back on so I don't trip. Whew. All right, so hopefully you can see the angles now, and I just want to point out what I did was I basically, and it's kind of got misaligned here, so let me fix that. In the dark, kind of got twisted there. Okay. So right about here, we see the beam comes in, hits this surface. The refracted ray, if you recall, is basically coming out parallel to the surface or just barely disappeared. And we can see this extra ray here is coming out somewhere right around 85 degrees, let's say, okay? There's some extra reflections and stuff going on here. Things aren't perfectly aligned, but I'm looking at this part right here, right about at 85 degrees. So my claim is we should be able to figure out the critical angle from this, and I've got a picture on the board because I guess right at this moment, this is the first angle where we get total internal reflection, right? There's no beam coming out. If I go to any other angle like this, whoops, the other way, we see there is refraction. Once we exceed this little spot here, it's no more refraction. All of it is internally reflected. Notice this happens when we're going from a high index to a low index. It doesn't happen the other side. All right, so let's go up to the board and take a look. Let me hit all the lights. Give me just a second. Hopefully you could see that on the screen a minute ago. And let's go up to board number 1. All right, so I've got this drawn up here. You can see this is the situation we had. And what did we discover there? I had a marker somewhere. There it is. We said that this entire angle right here was about 85 degrees. So that notice, I drew in the normal to the surface here at the semicircular lens, and so 2 times this angle, because angle of reflection, angle of incidence equals angle of reflection, so these 2 angles should be equal because it's reflected there. So notice 2 times theta is 85, so then what is that, about 42.5 if I divide that in 2, make sure I didn't screw that up, 42 times 2 is 84, yep, okay, good. So now, what we can see is I've also done the math over here for this interface. And this is where a lot of students get confused. We're used to sometimes talking about air into glass or air into acrylic. And so we're used to calling N1 air and N2 acrylic. But at this point right here, notice I'm talking about the first index is actually acrylic. So I would say N1 sine theta 1, which happens to be the critical angle. The refracted ray is just barely disappeared, so this is about 90 degrees. And so notice the second index of material is air, and then the second angle is 90. You rearrange that and solve for the critical angle, and we get an answer that's in pretty good agreement, right? You could do a percent difference on this, but I just wanted to point that out. I think that's all you need to know for that one. Oh, where's the stop video button? Oh my gosh. Hopefully that actually recorded. Oh my gosh, all these pop-ups all of a sudden. Just trying to stop this video. Where's the... Holy cow.